Here we go. Can you see?
Yeah, sure.
Oh,
You
nice.
closed your.
All
Thank you.
right. So first of all, thank you, Asif, for inviting me to this talk, and also to all audience. Thank you for giving your time, and I will try my best to justify your time. So you can see a very mesmerizing, say, image on the first screen. So you can see there are certain diffusion-like process happening here, and there are spreading and a very particular pattern is emerging there. So I will make two comments on this particular pattern. First of all, this is a non-linear system, something called reaction diffusion system. They are better modeled by non-linear physics. And there has been a recent attempt to tackle this non-linear system using quantum resources. I would say it's more like exploring this domain. Right. So today we will try to go into some depth, and before going into jumping into this non-linear system, I think it is also good to, or it is a good opportunity for us to uh, first go into the fundamentals like linear system, and then try to connect and build intuition for why quantum can also be useful in some spatial weakly non-linear systems. Here, so we have, so there is a pretty natural question. So I have my friend Jack at the left corner. So when I presented to him, he asked me several questions. So four important questions were, there are so many nonlinear systems. I mean, most of the systems, if you see, they are nonlinear. Then which system we are talking about? So we are talking about very particular system, right? And then coming to question two, uh, very natural question is quantum mechanics is linear theory. Superposition is possible due to that linearity. Then how one can uh, understand this particular, or build a intuition that quantum can be useful for nonlinear system also. Then comes the third question that I would say is very important to consider. So we will see that not all nonlinear system is tractable, uh, but there are certain very special of them. So the third question goes into what are those systems and under which spatial criteria or condition they can be tracked. Then pretty natural question: does it have any practical utility? Because sometimes we have some good theory built up on, I would say, that might not be useful in current or maybe future time. So we will also try to touch the fourth part, and we will see that it indeed it has some uh, good utility even in physics, engineering, and even in training machine learning models. Looks quite counterintuitive, but we will see that various special type of physical and engineering system, as well as various special type of machine learning model, has been explored using this particular pathway of quantum for non-linear system. So this is the context, I would say, I am trying to create. And before going further, I would like to have this talk more interactive. So I have both type of material. I would say the basic material, the fundamental, and also the advanced one. And I wish to, or I would like to have questions. If you find any basic things where you need certain support or help to understand, because I consider once we are very comfortable with the basic ideas, then going from linear to nonlinear systems won't be much hard task. So please feel free to interrupt me if you have any uh, question about the fundamentals. Yeah. So let us jump into the next segment. Yeah.
Manish, sorry to interrupt. Could you please click on the hide button from the sharing screen down?
Oh,
It's
sorry.
there,
Yeah,
right?
yeah.
I'm sorry. Please continue.
Okay, okay. Yeah. So my cursor is not visible here. Let me just see. Okay, so let me just go back and hide button. Is it okay now?
Yes.
Yeah. Good. Now it's working good, Asif?
Yeah, great, great.
Okay, yeah, yeah. So this talk is divided roughly into, I would say, four parts. So first part is even the genesis, from where these problems comes into picture, and it is better to look into higher complex system as a some sort of ladder-like a structure. We have the simple problem, simple algorithm for that, then a bit more complex, then again more complex problems comes into. Then in second part, we will see that most of the primitives that we have developed for linear systems are in fact sufficient to tackle some of the spatial nonlinear systems. So that we will cover in the second part. Third part, we will do uh, some sort of analysis. So several researchers has attempted this part, and me and my advisor, when I was an MTech student, also tried to develop a certain spatial techniques. So we will do a analysis of or comparison of how well all those algorithm work. Now practical utility will come at the end part. So now let us see the first part. The genesis will be with a very simple problem like Hamiltonian simulation, from where the physics of quantum, I would say quantum computation, I would say kicked into in yeah, and then we will look into quantum linear system problems. So linear systems are, I would say, in our maths class was very important part of a curriculum where we try to solve those problems. Then we will jump into quantum ODE, ordinary differential equation, of both types, linear and quadratic cases. Then we will follow quantum PDE problem, partial differential equation, and there comes the problem. The problem means reaction diffusion. That particular mesmerizing picture at very beginning was a very special type of reaction diffusion system, I would say. Right. Now, coming to the toolbox or algorithmic primitives, uh, Hamiltonian simulation algorithm has been explored since 1996 or even attempted by Feynman also. Then we will see quantum linear system solver. That was a big breakthrough in 2009 or around. Then we will see a very, I call it a very smart tool, something called linearization technique. So linearization technique, I think you might be able to guess or understand already that this will be the tool which will take any nonlinear system and try to convert into linear part. So we will see when to apply this and what does it promise when this is successful, right? Then comes the, all right, the attempts that has been made by several, or I would say at least three groups around the world. So first was tried by something called Euler method technique. Then Taylor method was used, and then we tried to do it using something called Chebyshev series method. We will see into detail what they are. So these are the content, and let us go into the genesis part. So you can see this particular quadrant, the last quadrant. There is very, I feel some sort of intimidating equation. There are so many terms there. Uh, so let us not go deep into it now. For us, it is what is important is it is a partial differential equation, and it has certain form like time part, space part, and a if or function part. So we will see some simpler thing. First of all, let us not go into that. Something called quadratic coding, which looks a bit less intimidating per se, uh, because here terms are distinguishable. Like you can see a left hand term and right hand terms. They're quite precisely written down and looks quite familiar at least. Yeah. Then even we can look for some more simpler things, something like linear ODE. You can see complexity is decreasing, and now it almost look like class 12th problem. Linear ODE. Yeah. Then comes very special type of linear ODE. Just a few questions to audience. Can someone recognize this first equation? A simple question, just to let me know. Yeah, the first equation is a quite popular and foundational result, I would say. Uh, Ashif, can you see some response in chat?
I think they cannot. I think nobody has responded.
Okay, okay, no problem. So we
But
can,
we can continue. Yeah.
correct, yeah. So this is Schrodinger equation, basically. We can see this particular
Yeah.
equation.
One of the
Yeah, yeah.
audience commented Schrodinger equation. Yeah.
Nice, nice. Thank you, thank you, thank you for that response. Yeah. So what we are trying to see here that to tackle the fourth quadrant, the reaction diffusion equation, we will try to envision or look or frame it as a quadratic ODE. We will try to relate it to quadratic ODE. Then we will see how quadratic ODE, which is a non-linear, not linear, can be related to linear ODE using certain device. And linear ODE seems much closer to the foundational equation of quantum mechanics, the Schrodinger equation, right? So this would be the attack strategy that has been developed by, I would say, the first person who attempted this field. Right, yeah. So we have this quantum Hamiltonian simulation problem. Uh, I will let me know how much detail you want. I will rush through it. So usually we have a matrix description for the problem and initial state, and there is a time given to us that we need the state vector at a particular time. Right. So usually these details are important that H, we don't worry about the details of like how H has been given. All we know that if I request a particular entry of H, then it will be given to me. Then my algorithm will act upon those entries and compute the result. Yeah. It's good to know because sometimes this oracle for H and oracle for phi could be a bottleneck. So good to know. Now, what exactly this epsilon approximate state vector time, which is some sort of output requirement. We need as an output epsilon approximate state vector. What exactly it means? So I visualize this as some sort of on Hilbert space, a ideal vector. We call it xi t, and epsilon is like a small sweet spot or circle. That epsilon is described by user itself, that how much accuracy it wants, and all we have to do is to find a vector within this particular circle. Then we consider algorithm as successful, right? So now jumping into the algorithm part, how people design this. So here is the Schrodinger equation, and closed formed expression exists to solve this differential equation because this is one of the simplest, I would say, comparatively. Yeah. Then now all we have to do is to solve this algebraic expression. So how exactly it is done? So if you translate this algebraic equation, that is xi t is equal to e raised to I iota ht, then basically it amounts to this particular geometric interpretation that you have vector somewhere and you have to go within certain sweet spot, right? So how it is done in practice? We in practice usually take this particular function, I would say metric function, and decompose it into several unitary matrices. So one matrices has been written as several unitary matrices, and those U1, U2 are basically quantum gates, right? So now you can see this particular picture, zigzag lag. So all the algorithm promise is that it will take you to the sweet spot, the green area. How it takes you should not be burdensome. So this is the, I would say, primer for the. So we have efficient algorithm for it, which depends on T and epsilon, and it has some query complexity. All it matters is that we have a efficient algorithm, quantum algorithm, to deal this problem, this quantum problem. Now coming to the ODE, now we have a good background. Now ODE would look like this, simple equation, and now requirements are same. We have been given a D sparse matrix A. Now this time A need not be Hermitian. Before in the last part segment, Hermitian is mandatory. Yeah, but here we don't need Hermitian. We will see how this is not a bottleneck or a problem. So requirements are similar. You have been given an initial state. Now challenge is find the system's state at certain time in future with certain epsilon approximation. Same oracle concept will be there that you have been given. You don't worry about how A is given. Someone will give you A and psi naught. Yeah. And I said U, sorry. Now, a very important thing to, I would like to pause here. There is a difference between array of number and a quantum state. Basically, important note is trying to capture that particular, I would say, dichotomy. That array of number given to us like V1, V2, Vn, and a state vector which encode, say, amplitude encoding or something, are not exactly same object. They are different. And this need to be, I would say, first of all, something we need to internalize for sure. And now moving to how ODE algorithms are solved. So bigger picture is this: you take the algorithm, the ODE problem, and there are methods like Euler method, Taylor series method, then spectral method. And if you do this particular pass through these particular methods, you convert this ODE problem into a system of linear equation problem. So one problem is converted into another problem. So this is very popular in, I would say, engineering, where you must have seen, like in famous spirit, something like finite difference method, finite element method. So there, I mean, it is some sort of precursor to those advanced techniques, I would say, where linear systems algorithms or casting the problem into linear system are done routinely. Yeah. Now, once we have the linear system algorithm, we solve it and we get our requirement, that is UT. Now, just to build intuition, I will let you know how exactly this particular ODE to linear system goes on. So this is very, you can see that particular picture where we have T naught, T1, Tn. There's a time, and then you have a equation written there. You can recognize the left hand side is nothing but derivative if h tending to 0. The calculus, old calculus. So this was the technique devised by Euler long back ago. So if you evaluate this equation at T naught, you will get a set of equation. At T1, you get another equation. At T2, then you get another equation. Then you have several linear system of equation, P of them. And then that's what we are naming as M by is equal to P. So now let us go to quantum ODE problem. So first of all, till now, equation was, there is nothing like quantum or classical distinction there, ODE problem. Now converting into a linear system, other problem. Now there is a very important concept, something called embedding the problem of linear system, generic one, to classical linear system problem. So you can see the difference here. It is written on the slide as C y vector is equal to V vector. Yeah. So you can see a particular M by is equal to B has been translated or embedded as another linear system. Now we don't have array like B by and B. We have a state vector, corresponding state vector, not exactly same, but related, I would say. That is, it is something called quantum embedding of problem. Now problem has been converted into, I would say, from classical world to quantum world. That would be my informal, I would say, statement, that problem has been now casted as a quantum problem. Now, once quantum problem has been is proposed, then we solve it using quantum linear system solver. So we will see more details about, but high level picture is this. ODE, then use methods and convert into linear system, then linear system to quantum linear system, and then you use quantum linear solvers. Yeah. Now going into quantum linear system. So this is very important slides. I consider this as very important slide to understand. I will consider the success of this talk as understanding our audience able to get at least a high level idea of this quantum linear system solver, because all quantum advantage we get for solving this problem are due to this particular efficient algorithm for quantum linear system problem. Yeah. So here it is the details. You will be given a problem, a linear system problem with get notation. You can see, and you will your matrix will be a sparse matrix. You will be given vector v, and goal is to approximate by vector. Now we use two indexes, n for matrix set, capital N, and kappa for condition number of matrix, a property of matrix. Yeah. Now quantumly, there is an algorithm, the best algorithm currently by CKS, by Child, Kothari, and Soma. Solve it in time proportional to log n. That is, I mean, the important to observe log n. D is the sparsity, K is the kappa, and then is the other factors. If we come into conjugate gradient, some sort of de facto method in general for this problem, then it scales as nd root k log as this. Key thing to observe is log n in CKS algorithm and capital N in conjugate gradient method. Yeah. There is something more to consider, very important. Please be careful here that QLSP, quantum linear system problem, and LSP are related but not exactly same problem, because output of both problem demands two different things. QLSP demand give me vector v, or let us say a state vector, quantum vector by. But LSP demand give me the array, some sort of array for y, capital Y vector. So they are different problem, and we are now currently interested or meditating on QLSP problems. Yeah. So QLSP problem is a classically hard problem in general. And the idea comes from something called BQP completeness of this problem. So for quantum computer, this problem is provably easy always, but for classical computer, it is not probably easy always. If we consider that quantum computation is more powerful than classical computation, then classical will choke somewhere for sure, but quantum won't. That is the BQP completeness mean here. It was very informal introduction to BQP completeness. Yeah. So now taking two notes that QLSP and LSP are different. For a QLSP problem, quantum computer can tackle it, but classically will find somewhere hard to tackle it. Now, just to sum up everything again, starting with the ODE, we convert it into the problems, and we reach the final requirement, that is state vector UT. Now, how to proceed toward our goal, the reaction diffusion equation? Then let us take one step, something called, let us try to assimilate quadratic case first of all. Yeah. So we have linear ODE. Let us try to assimilate the quadratic case using technique called linearization. Quadratic ODE are linearized and then solved. There are certain important criteria for it. We will look into those criteria for sure when this linearization is successful. Now we can bring our problem now, reaction diffusion problem. So reaction diffusion problem fits into this picture like this. Reaction diffusion, you do something called partial differential equation discretization. And then now we have the whole pipeline. So let me know any question you have. Just folks, I would like to know if everything is going well till now. Ashit, can you look for any question or query and let me
Yes.
know?
So yeah. So we will see. We don't have any questions.
Okay.
But we
Also, any thought about like whole flow diagram, like any if the audience feels somewhere we can delve into, or we can go into some more detail, then I will be happy to explain that particular detail in this particular, I would say,
yes.
flow chart.
I think we have a question from Shibu Meher. So he's asking, what does the product? I think he's asking about the power which is raised to function F2, which I believe is a tensor product.
Okay, yeah, correct, yeah. So, Shibu, this qt is basically I would say some sort of array of numbers. It's like it's not a scalar quantity, it's like a vector. It's not a scalar, sorry for that. And then powering a vector is basically here is realized using tensoring the vector. It's like similar to our idea in quantum. We have a state vector v1 and a state vector v2. We tensor there, and that become composite system. Yeah, similar spirit is there. Yeah. Good question, Sibu. Yeah. So now what I will do, I will go into two component, linearization and PD discretization. Linearization is something I guess would be new. PD discretization has been used in engineering. It's not a new invention, I would say, very routinely used. ODE methods and all other component, we will see into certain detail for sure as per our, we will see the time also. Okay, so I think we are good to go next. Yeah. Okay, so what exactly is the Kalman linearization? I would say the perhaps the key word, or I would say phrase of this particular talk, Kalman linearization. So what exactly promise after all? So promise is, if, for example, you have been given a quadratic ODE, for example, purpose, then it will convert into a infinite system of linear ODE. So this infinite system for linear ODE is as good as a single quadratic ODE. This is theoretical, or is a theorem. But infinite system of linear ODE, not a good thing for, I mean, computational, even classical or quantum or anything. Infinite thing not good to handle. Then we do here a compromise, something called finite system of linear ODE. We chop off, so we have infinite system of ODE. We just ignore certain part of it. I would say certain part of it means below everything is ignored. So 1 to infinity is there, a number of ODE. You just take 1 to 100 and ignore the other. Then now question is how to come up with that 100 number. Why not 200 or 300? So there goes the trade-off. The trade-off goes like this. If you take more number of equation out of the infinite system, then you try to go or reach the actual answer toward that particular actual answer. Your method is more and more accurate. And if you try to chop up a lot of terms, you just keep 10 terms or 5 terms, then it might be, you will be very offset by a large value. So there is a trade-off. Take more term, then your error will reduce, but more term means more computation you have to do. So there is some sort of trade-off. So this become a parameter of problem in something called truncation number. We will see into details. So just for sake of building intuition, I will show you how it is done. All right. So I think there is one line of statement that really is the spirit or key to understand Kalman linearization. So this linearization technique is basically a very smart change of variable, I would say. So what is change of variable? So you replace u tensor g, you can see in the power. So u is vector, which bold italics you can see, and you do this particular change of variable, and j runs from 1 to infinity. Now, this is all Kalman in his 1932 paper prescribed, and how it does really looks into. So if you embed this information or follow this prescription, then you get this particular metric equation, which is linear metric equation. You can see. So this is the, and also there is infinite size of the matrix is very apparent from the picture. Right now, if you are interested or curious about how this A11, A21, all those entries in this big matrix looks like, so they are block matrices. I don't have time to actually tell you all the details, but I would say, I mean, they are some sort of, all those A matrices are basically made from the F1 and F2, which is basically given in the main equation. You can see at the very top. So user input F1 and F2 matrices are processed as per Kalman linearization technique, and they are embedded into this sparse diagonal-like, almost diagonal-like, or upper diagonal.
Sorry for the interruption.
Yeah.
But there is a question, how will truncation impact the dynamics of the systems in C-line linearization?
I would say, right,
yeah,
correct.
Also, apart from this, I do have a question that how is there any quantitative measure for this truncation error?
Right, correct. So truncation error has been measured into something called ratio of this particular matrix F2 by F1. So they are matrices. We take their norm. Usually spectral norms are good. So your question is basically how to quantify that particular truncation error. So truncation errors are influenced by those F1 and F2 matrices, their spectral norms. If norms are very low, then it's almost like, so we can do this particular analysis. See, what we really want, we want this quadratic ODE. So this quadratic ODE would look like linear ODE if F2 matrix is not dominant. Correct or not? Could you just understand this part? If F2 matrix is not dominant over F1, I will define what is dominant means. But F2 parameter is very small compared to F1, then we can almost ignore F2. So this is the key idea that Kalman linearization, their convergence or their error truncation depends on how F1 and F2, their ratio behave. I would say the ratio is the correct word. It is matrix, then it is some sort of spectral norm and their ratio rather than matrix division. It's not that. So I would say the answer lies in how well F1 dominate over F2 is the factor that determines success of Kalman linearization. If F2 is highly dominating, means quadratic term will lead, and this truncation will need to be like millions or trillions down to the bottom. It's just for millions and trillions are for just a number to convince that large amount will be required. And opposite case, if F1 is dominant over F2, spectral norm, then you need just few of the Kalman terms, and then that would work. I mean, like 10 or 20, just for number purpose. Is it answering your question?
Yeah, I think it is addressing. And apart from that, Munib asked how this truncation will impact the dynamics of the system.
Correct. Yeah, correct. So, what is the name? Please, could you just repeat?
It is Munib. Yeah.
Munib, good question. So, Munib, what will happen if suppose F2 matrix is dominant over F1 and you truncate it at certain, say, T level, then what will happen? The dynamics, suppose you're interested in certain property of this nonlinear system. Say, for example, you are currently interested in its value u at T. Then what will happen? That particular u at T, the ideal one, and what you are getting after truncation will be very far apart. And due to this very far apart, some of the interesting feature of nonlinear system might not be able to captured by output that we get. let us call it UY output. If F2 is dominating and we have truncated it to a certain level, so for sure dynamics will be impacted, and some interesting feature of strongly quadratic ODE system might not be captured, or for capturing that interesting property of a strongly quadratic ODE, you have to take a lot of time. So this trade-off part will be there, and indeed some of the to capture more and more features of the quadratic ODE or quadratic system, it is very important to keep care of or take or consider where to truncate your series for sure. So this is my answer, Munir. Is it answering your question, or do I need to be more explicit, or there is something certain words that you are not able to understand? Munir, please let me know. Hello. Okay. Hello.
I think it is clear for him. I think.
Oh, Munir, yeah. So for some to just sum up, Munir, indeed, it will impact, and impact will be directly related to how strongly or weakly your linear system is. So usually, as a rule of thumb, weakly nonlinear systems are tractable. Tractable means you don't have to take too much of Kalman matrix terms. Yeah. So weakly, it is why the title is of the talk is weakly nonlinear system. Yeah. So that is, I would say, you can we can summarize like that to answer your question. Yeah. Yeah, we can discuss, Munif, later on also on this. So now, just to complete this particular flow diagram again. Now, what we will do, we have seen the linearization working. Now, let us go into PD discretization, which is, I would say, very routine type of task, but still let us see. So this is the equation, the problem that we are trying to tackle, and then what is this specification of problem? So the function on the right part, you can see f function which take input as u. If f is some sort of like something like quadratic function, then it has biological ecological importance. So the first image at the beginning of talk was that particular biological, in certain cellular or tissue like structure, that particular spreading of pattern to happen, something called Turing pattern. So that was the picture, which is a part of this special case called quadratic reaction diffusion equation. People have discussed or studied something like cubic case, quite I would say complicated relatively in pure physics way, and but for now we will restrict to the simple one, the quadratic one. Yeah, yeah. But analysis would follow, or one can bring or the idea from here to and inject into the cubic case also. So let us see what are the ideas. Yeah. So now we have seen a problem also. Now let us go to discretization. Yeah, right. Yeah, yeah, correct. Yeah. So basically, just to discretization are using like PDE to ODE are done using something like you have this particular line. So one question was about U. So U is a vector because you evaluate U at different positions like xj plus 1 and say several positions. And then you have this U vector in your hand. So this is a very routine task. People have done this task and convert. What happened? You have your equation and it get converted into a quadratic ODE. So this is how PD is converted into a quadratic ODE. Yeah. Now let us see where the innovation happened. Yeah. So basically, linearization part at the top. Two techniques are used, Kalman, and there is more one more technique, but Kalman is more popular and more amicable to quantum method. So there has not been much, I would say, progress the in that part. PDE discretization, no need to do that part. Now most of the innovation happen at this ODE methods. How to solve this? Because each of the steps are inquiring some error, linearization error, ODE errors. So every steps are adding some error. So we are trying to, our goal is to use very well precise ODE method. So usually what happened, people have already done in last year Euler method and then Taylor method. Then our group, me and advisor, proceeded towards something called matrix exponentiation method and pseudospectral method. Why? Because it has been seen that these methods are more sensitive, or I would say, it try to match or at least sometimes surpass our Taylor and Euler method in classical context. So our goal was to see how will it perform there also. Yeah. So now, what was the key hurdle that I faced, or I would say what was my contribution or our contribution was in this particular ODE, very top, d by dt is equal to ay. People usually don't bother about diagonalization of A. So no, basically you can read no as unknown. People don't bother about that. Then they use Euler and Taylor because that is very good method to apply when A's diagonalization is not known. But what we did, we tried to look into its detail of the matrix. Basically, the matrix right here, the column
Manish,
matrix. Yeah.
Sorry to interrupt, but I mean, we are
1
running
minute.
out of time.
Right.
So,
Almost covered. Yeah, I will just sum up now. So basically, we looked into diagonalization, which was not explored, and we found that diagonalization is possible under certain condition. And then these two methods were applied. So not going much into the diagonalization part, but our contribution was this to how to diagonalize this colossal matrix. We use certain template conversion, and then once we converted into this, we use certain technique like this was the criteria for success of this method. Under this criteria, we can have the particular algorithm, and then now both methods means this line. Method 1, method 2 was possible due to diagonalization that we did, and then last we have this particular result. No need to go into those details because so this was like comparative analysis, I would say, and at least you can see the last message is what we found that it is almost quite close to Taylor. If you look at, you ignore a polynomial factor, I mean like, n square is as good as n cube, like that. So it was almost surpassing. So that was the key message, I would say. And there are several open questions, I would say. And I would like to thank my advisor. It was a great help and fun to work with him. And I think I'm running out of time. So yeah, please let me know if you have any questions. You can pass me questions. I will be very happy to answer those. Yeah, in free time. Just let me know about in after this talk also.
Yeah. Thank you so much, Manish. It was great.